Hi everyone, my name's Laura McGregor and I'm the Product Marketing Manager at Zipsolve Analytical, and today I'd like to discuss the ongoing efforts to enhance GC/GC workflows for petrochemical analysis by addressing challenges in optimization, automation and data analysis through novel hardware and software improvements. Firstly, a brief overview for those of you who aren't familiar with Zipsolve. We're an instrument and solutions provider who are part of the Schoenberg Analytics Group alongside Marks International. Now, while Marks are known for their thermal desorption technology and sampling accessories, Zipsolve are more focused on the separation, including fast GC and GC times GC, as well as the detection with our time of flight mass spectrometers and the data analysis and chemometrics workflows. We do have offices and demo facilities across the world in Germany, China, USA and Canada, as well as our headquarters in the UK. And we work with trusted distributors across all other regions as well. And at Zipsolve, we've been involved with GC/GC for a long time, dating back to when the first generation of our benchtop mass spectrometers were introduced back in 2008. We've been dedicated to the continued development of the technology for both hardware and software to make it simpler to use and amenable to as many applications as possible, with the introduction of our flow modulator in 2017, as well as the dedicated GC/GC software with our Chromespace platform, and we continue to develop new technology. Just last month, we unveiled our latest offering, a cryogen-free thermal modulator, the Insight Thermal. So today I just want to explain how these tools can be used to improve GC/GC workflows for the petrochemical industry. Very briefly, to start off with, I'd like to do a quick synopsis of GC/GC. This is an advanced separation technique where we apply a second separation on a column with a different stationary phase so that we separate the sample based on two different chemical properties and pull apart compounds that would have collated in 1D GC. For example, it might be based on volatility and then polarity, or vice versa, depending on your choice of columns. But the key aspect is it's giving improved separation, so you gain greater insight into your sample composition. And the most essential part of the system is the modulator. You can't perform GC/GC without it. Its job is to preserve the separation from the first column, so it periodically traps the analytes as they elute from the primary column and re-injects them as narrow bands onto the short secondary column for further separation. And you can see from the schematic here, there's a side benefit in that we get much narrower peaks, which often boosts the signal to noise for better detection limits too. Then it's the job of GC/GC software to stack these slices side by side and merge the subpeaks together to form the 3D peaks, as you can see on here. So in order to perform GC/GC on an existing system, the key requirements are a modulator and the appropriate software. At Zipsolve, we now provide both flow and thermal modulators for GC/GC alongside our Chromespace software for both instrument control and data analysis. The Insight Flow on the left is a reverse fill flush flow modulator that was first released in 2017, and it's proven for a wide range of applications within both R&D and high throughput routine labs, such as for classifying hydrocarbons in jet fuel following the new ASTM method D8396. While our new cryogen-free thermal modulator, the Insight Thermal, shown on the right, delivers enhanced sensitivity and peak capacity, making it ideal for characterizing trace-level compounds in complex samples, such as looking for contaminants in novel fuels like pyrolysis oils. So what I'd like to do here is to show how each of these modulators works and then show some example applications within the petrochemical industry combined with the use of powerful software workflows. Starting with flow modulation. Now the key advantages here are that unlike thermal devices, there is no reliance on a cold jet to trap analytes, so they are consumable free, simply using differential pressures to fill and flush a sample loop. It also means that there's no volatility restrictions. Volatiles from C1 upwards can be modulated, expanding the application range for GCGC. Additionally, that consumable-free nature plus the simple valve-based design means that both the capital and running costs can be kept low. So it's often considered a good stepping stone onto GCGC. And finally, the precise control of flow in both columns also results in excellent repeatability, making it amenable to routine analysis and large sample batches. And as I said, we offer the Insight Flow at Sepsolve, and it uses reverse fill flush operation for complete transfer of analytes from the first column to the second column, and you get sharp symmetrical peaks. It can tackle the widest possible volatility range from C1, with the upper limit only restricted by the choice of column set. From the photo here, you can see that it is a small device. It's roughly the size of a €2 coin, and it bolts neatly onto the side of the GC oven using the mounting bracket that's in the photo. And that mounting bracket is capable of accommodating 2 Insight Flow devices for dual channel GCGC, or an optional 4-port splitter, as shown on the photo here, for parallel detection. And you'll hear more about both of those in a moment. So how does it work? Well, the Insight Flow uses a 5-port design with the 2 ports that you can see on the top of this animation actually welded onto the back of the plate. So that's why you can't see them in the photo in the top right. So the analytes come into the central port of the modulator and they begin to fill the sample loop. The modulation valve then switches position to quickly flush the contents of the loop onto the second column for further separation, and this happens in the reverse direction to which it was filled. Hence the name reverse fill flush. Now, the process happens alternately throughout the run to provide modulation of all of the components in the sample, and it's important to note that that flushing step happens very fast. It uses high flow rates through the 2D column to flush the analytes on and compress the chromatography for the second separation. The reverse fill flush method means that there's no way for the analytes to break through onto the second column. If the loop is overfilled, the analytes would be directed to the bleed line on the left-hand side, and this bleed line can be connected to an FID to ensure that there's complete transfer of analytes. But in reality, the flow calculator that we provide ensures that you won't overfill the loop. I should also mention that that loop volume can be changed too for more flexibility in method development and the column sets that can be used. So an additional advantage of the Insight Flow modulator is the excellent repeatability of both retention times and peak areas. And this is owing to the precise flow control in the primary and secondary columns, as well as the complete lack of moving parts outside, with the exception of that high-performance modulation valve, of course. And you can see here 8 injections of diesel that were performed each day over 3 days, and the retention times and areas for 5 analytes across the chromatogram. And you can see we've got high levels of repeatability, which has always made flow modulation a great fit for routine analysis. Another key advantage of flow modulation is, of course, the efficient modulation of volatiles. Because we're simply filling and flushing a sample loop to provide modulation, there's no volatility restrictions. The very volatile species can be modulated as efficiently as semi-volatiles, and that makes it a good fit for a wide range of petrochemical applications. In the example here, I've shown a close-up of a naphtha separation, where there are 2 very faint peaks at the beginning of the chromatogram that are highlighted by the red box and then shown in a zoomed in version in the surface chart. And these are identified as 2 C4 components, butane and isobutane. So being able to analyse these without the need for liquid cryogen is a big advantage of flow modulation. Equally, the lack of volatility restrictions also extends to the opposite end of the scale and the high boiling point analytes. And here we can see the GCGC FID chromatograms for marine oil at the top and then an alkane marker standard below it. And it shows that the analysis of high boilers like C50, C60 plus is easily achievable with flow modulation. The alkane standard itself also highlights a side benefit of GCGC, which is the structured ordering of chromatograms, because you can see that the N-alkanes all elute in a band along the bottom of the chromatogram, making it much simpler to perform group type analysis of samples, where we sum the peak areas of an entire chemical class and report these as a group. And you can see an example of that group type analysis here, where stencil regions can be drawn around the chemical classes, and then the peak areas of any peaks that elute within those regions are summed together for reporting. And in this case, we're showing a marker standard that was analysed for the new ASTM method D8396, and this is based on flow modulated GCGC FID for speciating hydrocarbons in jet fuel and other middle distillates. And in this case, we've got a reverse phase column set installed. So we have the paraffins and isoparaffins eluting later in the second dimension along the top of the chromatogram this time, while the aromatics elute earlier. And this method is for robust group type analysis of these key hydrocarbon classes that are shown by those coloured regions. And the stencil regions themselves can be created and saved easily in the ChromeSpace software. And using the marker standard, you're able to pinpoint where the classes elute, and then apply that same stencil to real samples, like here for an aviation fuel. And you can see that we've optimized the separation to get distinct groupings for the different chemical classes. And then the software can easily report these, like so, in an area percent table. Now, the repeatability of flow modulation is a good fit for these routine high throughput applications. And Insight Flow can take this a step further, as we can use dual channel GCGC with FID to double the productivity. And that's where we've got two Insight Flow modulators installed in a single oven with dual channel injection, two column sets and two FID detectors. So it means that two samples can be acquired simultaneously and processed by ChromeSpace software. So it doubles productivity while minimizing the use of lab space. And this configuration is already a proven accredited solution that we do have in operation in numerous environmental contract labs for analysing total petroleum hydrocarbons, but now we're expanding it to this new ASTM method for middle distillates. And I should say that group type analysis is really the norm for petrochemical separations. So in the software, we've added the flexibility to make these stencil regions as simple or as complex as required, depending on your samples. Like in this case, for a diesel run using a different column configuration, we can see that the stencil is far more detailed, and all of these individual regions are going to be reported. Now, staying on the ChromeSpace software for a moment before we go back to the flow modulator, we've added a few tools to help specifically with group type petrochemical analysis, so I just want to show you some of these. The first of which is our manual alignment using what's called a splining algorithm. And here, if your homologous series aren't eluting in a nice straight band, like we can see in this case for the N-alkanes that I'm just highlighting, it can be more difficult to draw the stencil regions. But what we can do is select the prominent N-alkanes in the alignment tool and use these to correct all of the second dimension times, like so. Now, that means that you can work with the new chromatogram to draw your stencils, and it's easier to draw around the different chemical classes. And just to show you how easy the group type workflow is, I've got a short video here that I captured using Chromespace software on my own laptop. And that's why in this version, you'll see that there's no instruments in the panel on the right. If this was the instrument PC, you would see a GC, modulator, and detector listed in this panel. If we look at the Chromespace homepage, you can see the different aspects of the workflow for both qualitative and quantitative analysis, as well as the sequencer. And what I'm going to do here is just to open up one of the aviation fuels. So when I open this, it's opening in the linear view, and we can immediately see that perhaps some baseline correction is needed in this case. So I'm going to apply the top hat algorithm, and you can see the new version that's created. There's an immediate benefit. We've removed all of that high baseline. So I'm going to work from the corrected version from now on and move over to the colour plot. We can interact with these colour plots, zooming in on sections. It recolorizes the peaks so we can see them more clearly, but we can also easily enhance the colour and change the colour palette completely if needed. So if we want to do group type analysis, we can select the stencils tool here. You are able to draw lines and text as well as regions, but in this case, I'm going to drag a region and it immediately pops up to ask what I want to call that. So we can enter the name and then we can resize this region to fit the chemical class that we're interested in. So in this case, drawing it all the way around all of these monoaromatics. And we can further customize this, changing the fonts, the color schemes that are involved, like so. And we can even exclude regions. So if we wanted to ensure that the column bleed wasn't reported, we can take that as a region and then simply tick the box to exclude it. So that means it won't be considered when we're reporting the integrated peak areas. Once you're happy with a stencil, you can save it. But for this example, I'm just going to remove those stencils that were created and load one that I made earlier, which you can see here that has all of the groups that we use in the ASTM D8396 method. And when you've got lots of regions, we've got this tool to be able to reorder them so that they're reported in the order that you want. And you can select a specific region to then change the annotations or the color more easily. We can then go on to integrate. So we'll just use the same integration settings in this case for all of the regions, but you can select individual integration settings if needed by just selecting the region of interest from the drop-down menu there. We can also select a hierarchy where we can group regions together and report them as a total. So we've got all of the individual N paraffins as regions, but we can simply tick the total N paraffins group there to ensure that they're reported in a total as well. So that makes the reporting easier. So once the integration's been performed, you can see that you've got your peak table with the areas and area percents for each of the regions of interest. And anything that is within a stencil boundary is reported. So anything that has a peak apex marker within a region will be reported as belonging to that region because we're integrating based on the linear data, like you can see there for the 3 summed subpeaks. So even if the tail of a peak is outside of the boundary, it means the entire peak will still be reported as being part of that stencil. So once we save our method, it means that we can apply it to individual samples by simply selecting that method when we're opening up the file so that it automatically gets applied on opening and you've got your area percent table ready. Alternatively, you can set this up in a sequence so that you can process an entire batch of samples using that method and have the reporting out to PDF at the same time. So it can all be done automatically. Now, based on the examples so far for flow modulation, it clearly has a lot of advantages, but one of the limitations has been that it's often thought of as more complicated to use. And this doesn't have to be the case. Previously, when using flow modulated GCGC, the bleed line would need to be altered when certain parameters were changed, and that made method development a bit more time consuming. In this case, we have a bleed line control kit that's been included for Insight Flow to prevent the need to update the bleed line when there are regular changes to the column configuration or during method development when flow rates are frequently altered. So this is basically a back pressure regulator for the bleed line to ensure that we fill the loop at the correct flow rate no matter what columns are being used. So it eliminates the need to trim the length of the bleed line capillary to get the right restriction to get the correct flow. So we're simply adjusting the back pressure with an auxiliary pressure source and easily adjust the flow by setting a back pressure. So that makes it really useful for labs looking to change column configurations regularly, for example, as part of method development. Finally, the high 2D flow rates that are used in flow modulated GCGC can actually be seen as both a limitation and an advantage depending on your application, because the flow rates are often considered too high to couple directly to mass spectrometers, although there are configurations available to allow this to be done successfully, and we have indeed done this with our benchtop 2 MS. But alternatively, the flow can be split between two detectors. And this parallel detection is simple to configure using flow modulation. For example, it may be the combination of MS and FID, or other single channel detectors like sulfur chemiluminescence detection, or SCD, like in this case. So it means you can capture two datasets with complementary information in a single analysis, as the sulfur species do tend to overlap with other aromatics in petrochemical separations. So having SCD means that we can do more precise group type analysis of just the sulfurs. And you can see that here, where the SCD at the top provides the selectivity required for more robust measurement of these classes. So we can be confident about the quantitative values, while retaining the FID data for the more general hydrocarbon classification. And we can, of course, do this parallel detection with mass spec using our own benchtop 2 that you can see pictured here. So it means that in addition to quantitation by FID, the mass spec data provides identification and it makes it easier to define the stencil boundaries. So this is an example of road diesel that was nicely separated using Insight Flow with parallel detection by TOF-MS and FID, where we can see that the benchtop 2 provides reference quality spectra with accurate isotope patterns and powerful mass accuracy, less than 50 ppm, that adds confidence to your identifications, like in this example for one of the N-alkanes. And it's worth noting that we do provide a 4-port purge splitter, which we recommend when two detectors of different operating pressures are being used, like FID and MS, to ensure that a constant split ratio is maintained between the two detectors throughout the run. If we look at that example in a different view, just focusing on the chromatograms, you can see that we've got nice alignment of the two channels, and it means we can use the MS data to help identify compounds and help define stencil boundaries, which can then be applied to the FID data. So we can use EICs to find the peaks of interest or classes of interest, or we can create simple scripting expressions, like here, to find particular classes. In this case, the C2 alkyl naphthalenes. So the expression is creating a new clean chromatogram that shows only the peaks that pass that expression. In this case, the MZ156 and MZ141 have to be within the top three most intense ions within the spectrum. And it means that now that we've defined that class, we can draw a stencil around it, and then we can continue to build up a stencil that can be saved and then applied to the FID files for quantitation of those classes. And we can take that a step further and use multiple scripts at a time to classify a sample, like you can see here, where the coloured markers represent a chemical class assigned to the peak. And once again, these are software tools that can, of course, be used with both flow and thermal modulation, even though I am showing them applied to the flow modulated data in this case. So moving on to the thermal modulation, here the analytes become enriched in the carrier gas, while in flow modulation they're effectively diluted in the high 2D flow rates that are used. The jets also provide focusing to produce sharp, narrow peaks and greater boosts in sensitivity. And those sharp peaks also help to improve the peak capacity for enhanced separation of the most complex samples. And finally, it's often thought of as being simpler in terms of the method development, though recent improvements such as the bleed line control kit that I just mentioned have gone a long way to improve flexibility of flow modulation. And generally, there are two types of thermal modulation depending on how the cold jet is cooled, either cryogen-free using a chiller unit or with liquid cryogen. And the latter allows more volatile species to be modulated, but of course there is the additional expense of liquid cryogen and additional health and safety requirements. So what can CEPSOLV offer for thermal modulation? Well, we now have the new Insight Thermal, which is a cryogen-free thermal modulator using delay loop technology. So that means that the column loops between a pair of jets within the GC oven, and these jets use cooled and heated gas, either air or nitrogen, to alternately trap and release the analytes. And as I said, it is cryogen-free, so it uses a chiller unit to do the cooling of the gas rather than liquid nitrogen. And you can see that chiller unit under the bench in the photo on the left. And on the right, you can see the column holder here, which holds the loops of column in place between the cold jet and the hot jet. So if we zoom in on this region, I'll just show you a little better what's happening to provide the modulation. Now, first of all, the cold jet is always on. So as the analytes elute from the first column and enter that first modulation loop, the cold jet will trap them. The hot jet then pulses on for a short time, and that deflects the cold jet and releases the analytes, where they make their way round the loop onto the next cooling stage of the modulation process, like you can see here. So they move to the second point that passes between the jets, where the process repeats. They're once again trapped by the cold jet, and then the hot jet releases them. So we can see that now they make their way onto the second column as a narrow band, and unlike flow modulation, where we use high flow rates in the second column to compress the chromatography, here the focusing is achieved via the jets, and the analytes become enriched in the carrier gas. So you boost the sensitivity. And that's always been one of the key advantages of thermal modulation. You get sharp, narrow peaks for greater sensitivity and greater peak capacity for better separation. And in terms of the Insight Thermal, one of the key advantages of the system is the integrated control within the ChromSpace software. you're able to sequence sample analysis and leave it running unattended, even if you want to run different sample types using different methods and modulation parameters. And you can see an example method on here. So it means that you've got confident, unattended analysis and simpler, more flexible method development because you can leave samples running under different conditions. And in the method that you can see here, you've got full control of all the modulation parameters with variable modulation times and ramped rates for the hot jet temperature and cold jet flows. And this is something that's extremely important, because it means that the cold jet flow can be ramped down as the run progresses, while the hot jet temperature is ramped up. So that means we can extend the range to look at high boilers, like you can see in this vacuum gas oil sample. Because without this, the high boilers would get irreversibly trapped by the cold jet, and that's been a well-known issue with legacy thermal modulators. And just to emphasize the importance of it, you can see in the examples here the difference between running with and without ramped cold jet flow rates. This is actually data that was published almost 20 years ago using a modified modulator, showing the impact of controlling the cold jet flow rate on just the C24 to C36 region of a chromatogram. The one on the left uses a constant cold jet flow rate of 17 litres per minute. And this high flow rate made the trapping temperature too cold, and it meant that not all of the trapped component was launched efficiently by the hot jet. And you can see that tail across the chromatogram, to the extent that you begin to lose the larger components completely. While on the right, a ramped rate was used to decrease the cold jet flow rate as the run progressed, and you can see that the chromatography is much improved. You're going to be able to capture more information and correct quantitative values for those higher boiling point components. And the Insight Thermal has that ability built into its design, with linear ramps fully automated within the ChromeSpace methods. And the results of this are obvious with the excellent chromatography that you can see across the entire chromatogram here for a vacuum gas oil and efficient modulation of C50 plus. Another limitation of legacy thermal modulators had been that it was quite challenged to install the column set and to ensure that the loops were well aligned between the jets and stayed well aligned throughout analysis. And here, the design of our column holder, which is patent pending, resolves this issue. It can be removed from the device to allow installation of the column outside of the GC oven, and the figure of 8 design basically locks the loops in place as the column is wound around the holder. So that means that it can be installed quickly and easily. And if we zoom in, on the front of the column holder, you can see these small grooves that also help to secure the loops in place and keep them precisely aligned when the column holder is slid into position. So the loops can't move during or between analysis, and it provides improved reproducibility for thermal modulation and makes it more amenable to routine analysis. And further helping the use of thermal modulation in more routine types of analysis is the control of the jets that we have, because another previous issue had been the reliability when using unattended analysis. So here, excessive cold jet flow rates can cause issues between runs or between sequences when the oven temperature is low, because the cold jet will freeze any moisture in the air and form icicles. But here, we're using a default standby flow to the cold jet of just 0.5 litres per minute to provide the confidence to leave those sequences running overnight or over weekends. Because this minimal value means that even between runs or between sequences, there won't be any icicle formation or any downtime. So we've left this running over long weekends and there's been no icicle formation. And the proof of performance of this modulator is really in separations like this, where we've got a light crude oil run using Insight Thermal with GCGC FID. And you can see that we're really maximizing the use of the separation space with the thousands of components that are present, and excellent chromatography from the start to the end of the run across a wide volatility range. And that's again thanks to those cold jet flow rate ramps to gradually decrease the cold jet flow rate throughout the run. And there's also good distinctions between the key chemical classes that you can see here for robust group type speciation of them. And that level of separation is also important for the research and development of novel fuels such as pyrolysis oil, where trace contaminants must be identified because they may impact the quality of the oil and its applicability. And that's a job well suited for thermal modulation. In this case, we can see a 3D plot of a pyrolysis oil from mixed waste plastic, and that's analysed by GCGC with the benchtop 2. And this view gives a good perspective of the varied intensity and range of analytes involved. And highlighted in the centre of the magnifying glass at the bottom of the image, you can just see a small peak that in a 1D separation it would have eluted at exactly the same time as all the other peaks directly above it, making it very unlikely to be detected. While here, we can see it's well separated and confidently identified against a reference library to give the above match. And importantly, it is a chlorinated compound that may impact the quality of the oil and its applicability. So it's vital to achieve this level of detail in the research and development of these novel fuels. And the search for these trace contaminants can be simplified by software tools like the scripting expressions that I've already mentioned. In this case, we've got a pyrolysis oil from scrap tires in the front plot, and then at the back we have a filtered chromatogram using a scripting expression to search for any sulfur containing compounds. And these filtering scripts, like you saw earlier, can be specific to an individual compound or class, or they can be broad to search for distinctive isotope patterns like chlorine, or for the neutral loss like shown here for sulfur. So in this case, a new filtered chromatogram has been generated that shows only the peaks that pass the expression, and it makes it easy to find the compounds of interest, even if they are at trace levels and co-eluting with other components. So hopefully this presentation has shown you that both flow and thermally modulated GCGC can give powerful results for petrochemical analysis, with the choice of device being decided based on sample volatility, complexity, required detection limits, and budget. And at ZepSolve, we can provide the Insight range of flow and thermal modulators and guide you to the best configuration to fit your requirements, as well as provide easy workflows using the Chromespace software for fast group type analysis, as well as screening for trace contaminants. And the Insight modulators can of course be provided as standalone systems to upgrade existing GC platforms, but can also be integrated into our full end-to-end workflows, like those including the benchtop 2 mass spectrometer. So if you are wondering what GCGC can do for you, then please do get in touch and we can advise on the best configuration for your samples. So that brings me to the end of this presentation. Thank you very much for listening. If you do have any questions, we'll hopefully have a little time for these now. Otherwise, you are welcome to get in touch using the contact details shown on the slide. So please type in any questions into the question box now. Okay, we have a couple of questions here. First one is, when you're using SCD, does the software also provide instrument control? Yes, Chromespace will be able to control the full system and provide data analysis when using SCD. We can do this with parallel detection too, so we do have some customers going as far as collecting 3 different datasets in a single analysis. That's with TOF, FID and SCD all connected in parallel. So there's a lot of flexibility there. We've also coupled our GC-GC modulators with a lot of other different detectors as well, like single quadrupole MS, Orbitrap, QTOFs, AED, ECD. So in terms of some of these other detectors, we may be unable to provide full control through ChromeSpace, like for third-party mass spec platforms. So in those cases, you would need to utilize 2 software systems for control, but ChromeSpace is still then able to process the data from all of these platforms. You just do it offline. And we do have customers already utilizing our GC-GC with all those different configurations. The next question we have here is, what other applications can GC-GC be used for? Well, I've shown a lot of examples here for petrochemicals and novel fuels, but another related one that we've been working on a lot recently is the analysis of recycled materials, specifically looking at odors from recycled plastics. And this is where odorous compounds might remain in the plastic after the recycling process and then may leach into the food or drink samples that the plastic goes on to package. So we've developed a solution using thermal desorption with GC-GC TOF MS to separate the odour compounds away from the dominant aliphatics that are in these samples to determine whether the plastic should pass or fail quality control. And the beauty of this approach is that the odour compounds can be identified, so then the recycling process can be updated to prevent the issue from happening again. So that's another important application we've been seeing a lot of recently. But of course, GC-GC is also used in a huge range of other application areas, from environmental analysis, where you're dealing with a range of complex matrices, such as oil spills, to flavour and aroma analysis in food and beverages, and even in human health too, like applications such as metabolomics or biomarker discovery for non-invasive diagnosis of diseases. So it really is used to tackle a lot of different challenges. So I think that's all the questions that we have so far. If you do think of anything at a later time, or if you're watching this on demand, then please feel free to reach out via the contact details that are shown on the slide. And thank you again for listening. Enjoy the rest of your day. Bye.